The Big Bang is a lie. The spectrum locked at 2 in the morning. A jagged drop where no drop should be. Someone whispered, 14. Nobody laughed. If that number held, we weren't just early, we were impossibly early. The room went quiet, then louder than any celebration. Because if a galaxy really sat at Redshift 14, the timeline we teach bends until it creaks. Here's the claim. The Big Bang timeline is breaking in real time. Webb's first deep fields didn't add detail. They punched holes in the map. Tonight we'll expose the measurement trap, the institutional spin, and what replaces the origin story. Rewind to frame 1. The impossible dawn, JWST's first shock. The first frames looked like any other deep field until they didn't. Small, red smudges, the kind we'd learned to ignore as faint background, lit up as if someone had turned a knob past reasonable. Teams ran photometric redshifts, the quick and dirty distance guesses you make from colors when spectra aren't in hand. The outputs came back stacked at extreme redshifts, 10, 12, beyond. Too many, too bright, too soon. Then came the hard test, spectroscopy. You don't argue with lines burned into the light, breaks and features mapped to physics, not wishful thinking. Some candidates slid down the ladder as spectra cut through dust and emission line tricks, but others held high. JWST GSZ14 became a shorthand for a problem nobody could wave away. A galaxy shining when the universe was roughly 280 million years old. Not a rumor. Multiple teams, cross-checked instruments, cautiously worded but decisive. On paper, lambdictum hadn't changed. Inflation seeded tiny ripples, dark matter collapsed first, gas rained into halos and cooled, stars lit, feedback fought back. Growth was supposed to be a long negotiation, not a sprint. At redshift 10 to 14, you expected small, blue, clumpy things, patches of first light, not confident beacons. What Webb showed instead were objects with inferred stellar masses that, even after conservative modeling, strained the schedule. If those masses were right, you had to pack 1 billion suns of stars, or the luminous equivalent, into windows we treated like buffer time. Meanwhile, sizes complicated the picture. Some sources looked surprisingly compact and bright per unit area, pushing against surface brightness expectations once you account for dimming with redshift. Lens models were pulled in immediately. Was magnification fooling us, turning rare into common? In a few cases, yes. Foreground structure stretched and boosted distant light, and reanalyses knocked some champs off the podium. But even after you applied careful lens maps and cut the show-offs, a crowd remained at the dawn. The selection trap snapped shut on cue. Photometric redshifts can be misled by strong emission lines that dump flux into broadband filters, making a nearer galaxy look farther and more massive. Dust can redden a closer object into a false ancient hue. Pipelines carry priors that nudge masses upward when templates assume later epoch behavior. Early press moved faster than caveats, and some headlines aged poorly. But Webb spectrographs, one night at a time, cleared away pretend elders and left behind a smaller, still uncomfortable cohort that refused to leave. Inside teams, realism replaced panic. If those masses hold at the high end, you compress growth. That means turning star formation efficiency up in dense, metal-poor gas, at least for bursts. It means letting initial mass functions skew top-heavy for a spell, front-loading light with short-lived massive stars. It means allowing periods of super-Reddington accretion around early black holes, where trapped photons fail to shove gas back and flows barrel inward. And it means acknowledging that feedback can delay star formation locally, then supercharge it when conditions flip, sawtooth histories instead of smooth ramps. There was a human beat in every plot. A grad student stared at a prism spectrum, tracing the continuum break, recalculating the uncertainty, asking the advisor if the fit could possibly prefer a lower redshift. Another team, weeks deep, updated a lens model, dropped a darling to Z-5, and opened a cheap bottle as both consolation and relief. Someone else stared at a postage stamp image and muttered about deblending nightmares. Because in crowded fields, One mesassigned pixel can move a mass by a factor of 2. Yet even with the caveats, the pattern stuck. Webb cut through surface brightness dimming with enormous sensitivity and resolution. It saw star-forming regions and nebular lines that Hubble couldn't reach. It found rest frame optical features with MIRI that pinned down redshifts from another angle. Every instrument that made the problem smaller also made it sharper. The dawn wasn't empty, it was busy. And that forced an uncomfortable acknowledgement. If the early map is crowded, maybe the map we used to navigate had the wrong scale in a few places. Not broken anchors, the big three hold, primordial element abundances, microwave background acoustic peaks, baryon acoustic oscillations. But the galaxy formation recipes that sit on top of that cosmological scaffolding need new knobs, new couplings, and fewer assumptions that late-time behavior simply slides backward. The stakes here are simple and personal. If those masses and timelines stand, then every course that taught galaxies grew patiently needs a red pen. Not to erase the story, but to tighten it, to remove the resting points we liked because they felt comfortable. Because if you want 1 billion suns of stars by 400 million years, you stop pretending the universe took its time. It didn't. So the cheers that followed that 2 a.m. spectrum weren't triumph. They were adrenaline, the sense that the floor had tilted and we were all reaching for the same handhold at once. And the handhold was the same as always. Get better data, strip bias, and when a number survives, believe it. Which brings us to the ruler itself. How distance can lie, why colors mislead, and how quiet calibration changes headlines after they've already been printed. The redshift trap, how distance can lie. To understand why a red number can wobble, start with how we get it. Photometric redshift is the fast lane. You measure brightness through a handful of filters, fit the colors to galaxy templates, and the code spits out a probability for distance. It's fast, it scales, and in the early JWST rush, it was the only way to triage thousands of smudges. But colors can lie. Spectroscopy is the sober friend who checks your Uber. A prism or grating spreads light into a spectrum and specific features. Lyman breaks, Balmer lines, O Roman 3, H alpha, lock the redshift. Why does photometry mislead? Strong emission lines can dump flux into a broadband filter, making a closer galaxy look redder and brighter than it is. Dust can redden a low-Z interloper into the disguise of an ancient source. Template priors, tuned on later epochs, can nudge fits toward higher masses when the true spectrum is dominated by nebular lines rather than starlight. In crowded fields, deblending can push light from neighbors into your target, inflating brightness and thus inferred mass. And everyone learned, painfully, that early JWST calibrations would be revised. Teams warned that initial count-to-flux conversions would tighten as Cycle 1 matured. There's a subtlety in the Lyman break method. At very high redshift, neutral hydrogen along the line of sight erases flux blueward of 1216 A ring in the rest frame. In photometry, you see a sharp drop between adjacent filters and infer break. But dust can mimic slope, and intermediate redshift galaxies with strong lines can fake steps. In spectroscopy, you model the continuum, account for line-of-sight absorption, and fit the break profile. It's slower, but it kills lookalikes. That's why confirmations at Z10 felt like turning a key in a lock rather than guessing the door. Then there's lensing. Foreground mass, clusters, groups, even galaxies can magnify background sources. Macrolensing stretches and brightens, turning rare into visible. Microlensing layers tiny boosts. Without a lens model, you can treat an outlier as common. JWST fields near massive structures demanded detailed mass maps. When groups updated models with NIR-spec redshifts for cluster members, a few record sources slid down or lost a chunk of inferred brightness. But lensing cuts both ways. It also lets us see fainter, truly distant objects that Hubble couldn't. The fix isn't avoidance, it's calibration. Surface brightness dimming adds another trap. Flux per unit area scales brutally with 1 plus Z4. JWST sensitivity punches past that, but selection then favors compact, high surface brightness regions, starbursts, clumps, ionized bubbles. If you assume smooth, extended light and derive a total mass, you can overshoot. Early pipelines that defaulted to later epoch size, mass relations learned to loosen those priors. When MIRI added mid-IR points, catching rest frame optical lines, fits snapped tighter. A few headline candidates stepped off stage. Enough stayed to keep the front row occupied. Dust isn't just a nuisance, it's a chameleon. At intermediate redshift, dusty starbursts can run redder than truly ancient galaxies. Without mid-IR points, a photometric fit can choose very far instead of very dusty. JWST's longer wavelength filters help, but at low signal-to-noise, the code's priors can dominate. That's partly why some early Z-16 whispers faded under spectra. The lesson was nothing is high. It was high isn't free. Teams also discovered how template choices steer masses. If you fit with star formation histories that rise smoothly, you'll distribute light across ages and inflate mass-to-light ratios. If you allow bursty histories and top-heavy initial mass functions in metal-poor gas, the same luminosity implies fewer, brighter stars, lower mass, higher specific star formation. Nebular continuum and line emission, often neglected in legacy templates, can dominate early spectra. Include them and apparent mass drops. Leave them out, and you hand fuel to the too big claim unnecessarily. Behind the scenes, quiet revisions rolled through pipelines. 0 points tweaked, background subtraction refined. Deblenders retrained on simulated JWST-like fields. Each change knocked a few candidates up or down. Press cycles don't wait for calibration notes, so public perception lagged the technical reality by months. Internally, most groups had the same mantra: publish the caution, show the posterior, flag the degeneracies, push for spectra. Still, some objects refused to budge. Spectra with clean breaks and mid-IR line detections pinned distances. Gravitational magnification corrected. Sizes measured with arcsecond care. Their light wasn't a trick of a line. It was stars and gas at impossible hours, shining hard. Those became the anchors for the argument that timelines needed compression mechanisms, not cosmology swaps. The stakes are clear. A shaky ruler draws a shaky map. If redshift is wrong, every downstream mass, size, and timescale collapses. But once you fix the ruler, spectra, lens models, calibrations, the remaining outliers aren't ghosts. They're guideposts. They tell you where the model's subgrid physics, not its global anchors, needs work. Here's the human moment. A postdoc who built their thesis on photometric catalogs stands over a NIRS-spec plot and watches a beloved candidate fall to Z5. There's a sigh, then a shrug. A different spectrum arrives and another source holds at Z12. The room claps quietly, because distance told the truth and now the hard work, explaining brightness without cheating time, can begin. The institutional spin, crisis management 101. While the spectrographs were doing their job one photon at a time, something else was happening in press rooms and Slack channels. The language started to shift. Surprising replaced impossible. Anomaly replaced crisis. You could hear the pivot inside phrases crafted for safety. Discoveries refined, they don't overturn. It wasn't deception. It was muscle memory, how big institutions manage shock without lighting the building on fire. Here's how that works. First, frame the tension as calibration. We're still validating 0 points. Pipeline updates are coming. True statements, useful statements, but also a damper on what everyone felt staring at clean breaks in mid-IR lines. Meanwhile, preprints with bold phrasing got headlines before referees got a say. Press teams caught between speed and caution defaulted to neutrality. If you were watching from the outside, it looked like whiplash. Impossible 1 week, routine the next. Inside, the contrast was sharper. In closed seminars, people argued hard about priors, mass functions, and the pathologies of photometric fits at low signal-to-noise. In public, the tone softened. The standard model remains robust. Another true statement if you're talking about the anchors. but the hedge grated on folks doing late-night lens models who knew exactly how much work it took to push a darling from Z12 to Z5. The grind was real. The press tone felt airbrushed. Budgets crept into the room without being named. If your lab lives on renewals, you don't ring the alarm without a plan to test it. More time on JWST reads differently when panelists weigh stability against novelty. So the messaging became careful. Tension as opportunity, anomalies as a path to better simulations, better instruments. It's not corruption. It's the way systems protect continuity. The cost is authenticity. Audiences smell the dodge when the words get too tidy. Archives have their own tempo. Corrections move at the speed of referees and re-reductions, not virality. A calibration note that trims masses by 30% will never outrun a clip titled "Webb broke the Big Bang." So you got a weird inversion, quiet technical progress that actually deepened the problem, fighting a loud narrative that said the problem had vanished. When a spectroscopic confirmation landed at Z10, it didn't trend. It just sat there like a ledger entry, changing futures without fanfare. There were human calculations behind every adjective. A PI with a multi-institution team won't call something a crisis on camera because junior people pay for that if it backfires. A communications officer won't headline "too massive" without a paragraph on selection bias because one misstep becomes a cudgel in the next hearing. Everyone knows the rules. Earn trust by sounding calm. The trap is sounding anesthetized when the data wants urgency. You could feel the split during Q and As. A student asks, "If these Z-12 objects hold, do our semi-analytics need a new mode?" The speaker says, "We're exploring parameter space," then off-mic admits, "Yes, likely." In the hallway, two folks trade preprints proving the same point. Even after downgrades, the early census is crowded. Back on stage, the slide reads, "Refining early star formation histories." It's not wrong. It's just smaller than what the room is thinking. Then there's the message discipline around the word crisis. Some love it because it funds telescopes. Some hate it because it invites bad faith hot takes. The compromise is tension, a word that asks for patience. But by late 2025, the Hubble Constant fight had crossed the statistical line where patience looks like denial to outsiders. JWST's Cepheid work didn't erase local measurements. It backed them. Strong lensing time delays nudged the same way. And the number that matters in rooms that speak statistics quietly hit the wall. ~5 sigma. That isn't drama. That's a point of no return for the vanilla fit. Here's the whisper everyone heard and few said out loud. At ~5 sigma, the old model is fine, just give it time, story expires. Not the anchors, not expansion. The tidy, one-parameter patches. Past this line, you either add real new physics or real new astrophysics. The pivot kept lagging the facts. You also saw a new tactic, pre-bunking. Teams walked through failure modes in public before results dropped. Here's how emission lines fake distance. Here's how lensing fools counts. Here's where our priors can bias mass. Smart, disarming, and oddly empowering, because when confirmations survived that gauntlet, they felt earned. The tone didn't change much, but the subtext did. If it passes this list, it's real. The platform mismatch made everything harder. Clips can mint certainty in 15 seconds. Corrections take 15 minutes people won't give you. Institutions try to cut their own shorts, skimmable explainers with charts that didn't insult the audience. Some worked. Most sank under the algorithm's preference for spectacle. Meanwhile, the best work went where it always goes. Archive at 2 a.m., then journals, then talks with bad coffee and good questions. So what do you do when the world hears nothing to see and the spreadsheets say, "We need new physics or new astrophysics"? You stop auditioning for virality and show your receipts. You say the quiet thing plainly. The anchors, light elements, the CMB peaks, bow aren't the problem. The galaxy recipes are. You admit that a model can be right in scaffolding and wrong in furniture. You own the gap. Because spin only works until the next spectrum drops. And the spectrum doesn't care about tone. It cares about where the break lands, how the lines stack, and whether the fit leaves wiggle room. Which is where we're going next. The three anchors that don't budge, why they matter more than any headline, and how they fence the playground where surprises are allowed. The three anchors you can't wave away. Before we pull any more threads, plant your feet on the parts of the story that don't move. Three independent anchors tie our picture of the universe together, and none of the early galaxy fireworks have snapped them. If you want to argue that the Big Bang timeline is a lie, you'll run headfirst into these. Light element abundances, the cosmic microwave background's acoustic peaks, and the baryon acoustic oscillation ruler etched into galaxy maps. They don't ask for your permission. They sit there like bedrock. Start with the birthplace chemistry. Big Bang nucleosynthesis isn't a vibe. It's a narrow recipe that predicts how much deuterium, helium-4, and lithium-7 the early universe could make in its first minutes. Change the density of ordinary matter and the deuterium fraction swings. Change the expansion rate and helium shifts. Observers go out, measure ancient gas in pristine clouds backlit by quasars, count deuterium to hydrogen ratios, and land in the same small box that the theory draws. That box, in turn, matches the amount of baryons the CMB infers. You can't casually toss that and keep the rest. The nuclear clock locked a time and a density that later measurements echo. Then the sky itself hums with a pattern you can't fake, the CMB acoustic peaks. Those wiggles in the temperature and polarization power spectra are fossil sound waves from the photon, baryon fluid before recombination. Their positions and heights encode the universe's geometry, contents, and age with infuriating precision. Slide the matter density, the curve moves. Add or remove baryons, the odd, even peak contrast flips. Tilt the primordial spectrum, the envelope bends. Planck, ACT, SPT, independent instruments, different systematics, came back singing the same song. The chorus says, nearly flat spatial geometry, specific baryon and dark matter fractions, and a well-defined sound horizon at last scattering. That horizon becomes a standard ruler you can follow forward in time. Which brings us to the last anchor, baryon acoustic oscillations frozen into the large-scale distribution of galaxies. Think of it as the CMB's drumbeat carried into adulthood. The same sound horizon sets a preferred separation scale in galaxy pairs. Map millions of galaxies across billions of light years, stack the statistics, and a bump appears at that scale. Different surveys, SDSS, BOSS, EBOSS, DAISY, have found it at different redshifts. You can watch the ruler evolve with expansion. When you fit that bow ladder alongside the CMB's early blueprint, the parameters lock together. You don't get to refit the kitchen while pretending the foundation is optional. Notice what these three have in common. They're not one lab's pipeline. They're not one wavelength, one instrument, one team's priors. They're different physics, different epochs, different faults. Yet they converge. On the baryon density, on the sound horizon, on a flat or near-flat geometry, on a specific growth history folded into lambdictum. That's why when you hear the Big Bang is broken, the people who actually stare at these plots arch an eyebrow. The anchors aren't the problem. So where do the shocks fit? Inside the fence, those anchors build. Early galaxies that look too bright don't rewrite the sound horizon. Crowded dawn fields don't erase deuterium counts. A stubborn Hubble constant tension may hint at new ingredients, early dark energy, exotic interactions. But any fix has to thread the needle so it doesn't wreck the peaks or the bow ruler. That's the discipline. You can add a pre-recombination tweak to nudge H. You can let gravity or dark energy evolve subtly. You can alter neutrino physics within limits. But you do it under the gun of 3 independent audits. Most speculative replacements die there. Here's the subtle punchline. The anchors say expansion happened, the plasma sang, and the chemistry froze. They don't say galaxies must grow politely. That part is on us. Our recipes, our subgrid rules, our habit of smoothing what probably burst. When JWST shows starbursts roaring earlier, compact clumps shining harder, or black holes gulping faster, the anchors shrug. They're not contradicted. They're complemented by a universe that hustled. Human moment. A theorist flips from CMB residuals to a JWST spectrum and laughs quietly. The peaks survive your panic, they say, then circle a mid-IR line that shouldn't be that strong so early. A survey mapper traces the bow bump on a wall plot, taps the ruler and says, "Whatever we change, this stays." Meanwhile, a chemist of the cosmos rubs their eyes after a long night fitting deuterium lines and sends a note. Same box as last year. 3 different rooms, 1 foundation. So upgrade the ship, star formation levers, IMF tilt, bursty histories, early feedback, growth channels. Keep the ocean, the expansion history, and its acoustic fossils. That's the honest way through. Anchors hold, surprises pressure the rules within the fence, and the meaning shifts from lie to lag. The story we told stalled. The evidence we hold didn't. Inflation under cross-examination. To understand why the sky looks so strangely organized so soon, go back to the move that set the board. Inflation. Not the pop culture explosion, but a sliver of time when space itself expanded outrageously fast. The pitch was elegant. It solved 3 headaches at once. Why is the microwave background the same temperature in opposite directions if light couldn't cross between them in time? Inflation says those patches were neighbors before being yanked apart. Why is space so close to flat? Stretch a curved sheet long enough and wrinkles smooth. Where did structure come from? Quantum jitters in a field get stretched to cosmic scales, freeze as tiny density differences, and later gravity amplifies them. Those ideas didn't land in a vacuum. The acoustic peaks we planted in the last section, those wiggles in the CMB, fit inflation's promise almost suspiciously well. The pattern prefers nearly scale-invariant fluctuations with a slight tilt. That's exactly what simple inflationary potentials give. The bow ruler downstream. Same origin story. In that sense, inflation has receipts. It turned quantum noise into the drumbeat the cosmos still carries. But put it on the stand and ask for the pen, not just the prose. What field drove it? What shape did its potential have? How did it end and reheat the universe into particles we know? The generic mechanism works. The details get squishy. The inflaton isn't a detected particle. It's a placeholder with many candidate potentials. Tweak the slope and you get small changes in the tilt. Tweak the curvature and you predict different gravitational wave backgrounds. The flexibility is both a strength and a worry. If many models can fit the same sky, are we explaining or accommodating? There's also the hunt for a direct signature. Primordial gravitational waves from those first moments imprinting a curl pattern, B modes in the CMB polarization. Several experiments chased it. One famously mistook dust for the signal. As of now, we have upper limits. That squeezes out some large field models that would have splashed big B modes but leaves a wide swath of parameter space alive. So the absence of a detection isn't a death blow. It's a diet plan. Inflation trims to quieter potentials. Then you find small curiosities in the CMB at the largest angular scales. A low quadrupole power. Alignments people nickname with more drama than they deserve. Hemispherical asymmetry in a few analyses. These are low-significance teases that could be statistical flukes. They could also be hints that the inflationary pen stuttered features in the potential. A brief interruption in the roll, pre-inflation relics that didn't quite erase. Sensible people mark them as interesting, not as torches to burn the framework down. There's another thread. Can we get the seeds without importing a bespoke field? Some proposals try to tie the initial fluctuations to gravity itself, or to quantum effects in curved spacetime, reducing the number of ingredients. Others explore early dark energy, or tweaks to the pre-recombination expansion that nudge the Hubble tension while leaving the peaks and bow mostly intact. These are active, cautious attempts to modify the prelude without wrecking the song. None are slam dunks, but they show the instinct. Make the initial script tighter, not looser. Meanwhile, the early galaxy shock we've been following pressures the handoff. Even if inflation wrote the right notes on large scales, you still need small structures to grow fast. Inflation doesn't build galaxies, it sets initial conditions. That's why the fast channels will get 2 top-heavy stars in metal-free gas, direct collapse black holes, super Reddington episodes, bursty star formation histories, matter. They're the ways the universe can take a given seed spectrum and sprint instead of stroll. Human Scene, a cosmologist who spent a decade on polarization maps, sits at a coffee-stained table with a galaxy formation modeler. The cosmologist traces the CMB fit with a finger. This part's pin, they say. The modeler points to a JWST spectrum. This part is. They trade jokes about inflatons and subgrid recipes, then agree on the only plan that ever works, constrain from both ends. Make inflation earn its simplicity, make galaxies earn their speed. The stakes land here. If inflation is right in spirit but wrong in detail, data will keep shaving models. If it's wrong in spirit, something else still has to solve the horizon and flatness puzzles and seed the right kind of fluctuations without tripping the anchors. Either way, the discipline remains the same. Thread the needle the acoustic peaks and bow hand you. Respect light element abundances. Fit the tilt. Don't invent a cure that poisons the patient. So when we cross-examine inflation, we don't stage a coup. We run a stress test. Keep the parts that predict what we've measured at insane precision. Pressure the parts that hide behind flexibility. And remember the boundary between cosmic prologue and galactic hustle. Even a perfect pen can't guarantee a neat first chapter if the actors improvise. Up next, those fast channels, the tricks nature uses to cheat the clock without breaking the ledger. Fast channels, how the universe cheats the clock. If inflation hands you seeds and the anchors fence the playground, you still need a way to grow forests fast. That's where the universe reaches for its speed hacks, the channels that compress assembly without breaking the rules you've already accepted. Start with the heavyweights, direct collapse black holes. In pristine, metal-free pockets bathed in a strong ultraviolet background, molecular hydrogen can't cool efficiently. Gas stays warm, resists fragmentation, and instead of scattering into many small stars, it can funnel inward almost monolithically. Collapse 100,000 to 1,000,000 solar masses straight into a black hole. No slow ladder of remnants. Now you've got a central engine that can light a quasar early and organize a galaxy around it. It's not magic. It's thermodynamics under unusual conditions, and those conditions plausibly exist where early halos cluster and neighbors flood each other with dissociating light. That engine pairs with a second lever, super Reddington accretion. The textbook limit assumes photons push back effectively, but if inflows are thick, turbulent, and partially trap their own radiation, the push weakens. Photons are advected inward rather than escaping to shove gas out. For a while, accretion rates can exceed the classical cap by factors of a few to 10. Not forever. Feedback will punch holes and self-regulate, but long enough to move a black hole across orders of magnitude in mass before the clock hits 1 billion years. Simulations show those slim disk phases leave telltale spectra and variability. JWST sensitivity at rest frame optical and near IR is starting to pry at those signatures in the early record. Meanwhile, the stars themselves can cheat. In metal-free, low-dust gas, cooling paths are limited, Jeans masses rise, and the initial mass function can skew top-heavy. That means more massive stars per unit mass formed, short-lived, blisteringly bright furnaces that pour out ionizing photons and supercharge nebular lines. Observationally, that mimics large stellar masses if you fit with late epoch IMFs and smooth star formation histories. Allow bursty episodes in different IMFs, and the same luminosity corresponds to fewer stars, younger ages, and lower total mass. The physics behind it isn't hand-wavy. Metals provide efficient cooling channels. Without them, fragmentation pivots. The earliest generations lived fast and died dramatic, feeding the next round with heavy elements and turbulence. Cooling itself gets a boost from environment. At high redshift, densities are higher, dynamical times are shorter, and halos shake each other for free. Molecular hydrogen still matters in pristine pockets, but once even a trace of metals and dust appear, new pathways open. Fine structure lines from carbon and oxygen radiate energy away efficiently, letting gas shed heat and collapse into dense clumps rapidly. Those clumps can light up in short, intense bursts, bursty star formation histories rather than smooth ramps. When you stack those bursts across clumps and mergers, you build light and structure in jumps that average out to impossibly early if your model only allows slow and steady. Feedback plays the villain and the accomplice. Early stellar winds and supernovae can blow out gas, quench star formation locally, and make a halo look briefly quiet. Then, as fresh gas rains back along filaments, conditions flip: lower angular momentum, pockets shielded from radiation, turbulence primed by past blasts, and you get a supercharged burst. That delay-then-surge dynamic makes compact, bright regions that JWST naturally selects. It also explains why some early candidates looked overmassive under smooth priors, and then slid into more comfortable masses when modelers allowed the jagged paths nature prefers. Stack these levers: seed big, feed fast, form top-heavy for a spell, cool efficiently in the right places, and let feedback set the metronome, and the timeline loosens without moving the anchors. You don't need galaxies to be quietly enormous. You need them to be intermittently outrageous. There's also the social life of early halos. At Z-1014, bias is king. The densest regions are densest by a lot. Halos assemble in swarms. Minor mergers, cold streams along filaments, and tidal torques reorient angular momentum and funnel gas. You get synchronized bursts across neighbors, reionization bubbles that grow and overlap faster than expected, and environments where direct collapse conditions form next door to starburst factories. Lensing occasionally gifts us magnified views of these neighborhoods, spectra that show both young stars and hard ionizing sources in small volumes hint at this choreography. The impossible dawn looks less like lone skyscrapers and more like construction cranes jammed into the same block. Microstory: a team toggles an IMF prior in their SED fits from Chabrier to a top-heavy variant allowed in metal-poor gas. The inferred mass for a Z-12 candidate drops by a factor of 2, the age tightens, and the nebular lines finally make sense without exotic dust. Someone exhales. Then they push a Super Reddington prior into the black hole growth model for a neighboring source, and watch the accretion history hit the target luminosity within a few 100 million years. The whiteboard fills with arrows, not because the cosmos cheated, but because the code finally let it sprint. None of this erases the need for discipline. Each fast channel predicts signatures, ionization parameters, line ratios, X-ray limits, sizes, duty cycles. JWST, ALMA, Chandra, and future arrays will overconstrain them. The point is simple. When you let the early universe use the tools it actually had, pristine chemistry, clustered environments, violent feedback, and fat inflows, you don't have to break the ledger. You just have to stop assuming it balanced politely. The rendering vibe: efficiency, not fakery. By now you've seen the pattern. The universe doesn't waste moves. It grows fast where it can and ignores details nobody can ever ask it about. That's the rendering vibe, not that a programmer flips frames on and off, but that physics favors efficient encodings over full resolution everywhere all at once. Constraints don't just limit, they guide what becomes real. Start with bandwidth. Light speed caps how fast information travels. Horizons carve the universe into patches that can talk and patches that can't. Within a causal patch, facts stabilize because signals bounce, interact, and get copied. Outside, the details are out of reach. Efficient reality means you only instantiate correlations that can be accessed and redundantly recorded. That's decoherence on a grand stage. Alternatives collapse where information can leak and be checked. No leak, no objectivity. It's not metaphysics, it's the bookkeeping of entanglement. Now fold in an accounting rule with teeth. Landor's principle says erasing one bit of information costs energy as heat. Memory isn't free. Any world that writes every microdetail everywhere would fry its own ledger. Nature picks sparse descriptions that answer the questions observers can physically pose. Coarse graining isn't laziness. It's survival under constraints. Black holes shout the same lesson. Their entropy scales with horizon area, not volume. That's the holographic hint. Boundaries carry the count of possible internal states. If the degrees of freedom you can ever access scale with surface, not bulk, then full volume bookkeeping is overkill. You keep boundary data and reconstruct interiors when needed to the precision any measurement allows. Efficient, not fake. Decoherence and redundancy turn fragile amplitudes into stable facts. A chair becomes a chair because trillions of photons scatter off it into zillions of directions, encoding the same position and color in many channels. Many witnesses, one story. That redundancy is expensive, but only where people can look. The cosmos spends bits where interrogation is possible and lets symmetry and dynamics compress the rest. This is where rendering helps as a metaphor. Think of lazy loading in software. Assets stream in when the player enters a region. In physics terms, outcomes get fixed where interactions spread information irreversibly. No central server, no cheat code, just local rules stabilizing states when the environment can't keep them coherent. The timeline you write from those events is smooth because decoherence is brutally fast for big things. The mystery isn't why the world looks classical. It's how anything stays quantum long enough to matter. Area-bounded information changes what emptiness means. Voids aren't missing textures, they're low-information interiors that demand little storage. The action lives on edges, filaments, shocks, ionization fronts, where gradients allow signals to propagate and be measured. That's why the cosmic web looks like an efficient compression, sharp where it counts, smooth where it doesn't. JWST's dawn crowding fits this logic. You don't need everywhere to be bright. You need bright where causal neighborhoods can stabilize records quickly, dense knots, clustered halos, short dynamical times. Efficiency leans into clumps. Meanwhile, surface brightness dimming and selection cut the view toward compact, high-contrast regions. That's not a bug in the cosmos. It's an instrument bias that accidentally highlights where the universe already spends bits. Starbursts, nebular lines, tight sizes, those are redundancies in the making. We saw them first because both physics and hardware steer attention toward what quickly becomes objective. Here's the twist that keeps the metaphor honest. Efficient encoding is not simulation. Nobody saves compute by cheating the math. The math itself enforces thrift. Landmines sets energy costs for overwrites. Horizons limit addressable space. Decoherence anchors facts only where witnesses exist. Holographic bounds cap total distinctness inside a patch. These aren't aesthetic choices. They're constraints that make certain appearances inevitable and others unnecessary. Human beat. A student toggles an on-sky simulator with and without mid-IR lines. With them, a Z-12 candidate's SCD collapses to a tight solution. Without the posterior sprawls, the student laughs. It's like the spectrum asked for the detail, they say. The advisor nods. And we paid for it in photons and time. Quantum Darwinism wraps this up. Objectivity emerges when multiple environment fragments independently carry the same information about a system. JWST, ALMA, X-ray observatories, they're just very fancy fragments. When they all read the same story from different channels, the fact becomes public. The cosmos renders by consensus of interactions, not by decree. Add one last constraint, a finite storage quota for any horizon-sized patch. If information scales with area, there's a hard cap on how much distinct detail can ever be stabilized inside your worldline. Try to stuff in more, and physics pays you back with heat, collapse, or diffusion. That quota doesn't shrink meaning, it refines it. The universe invests in redundancy for the variables that drive futures and lets the rest ride on symmetry. So when Webb lit the dawn with compact, outrageous beacons, the vibe was this is fake. It was this is where physics spends. Hard constraints, speed of light, Landmines cost, holographic bounds, decoherence times steer the look. Anomalies are pressure on rules, not proof of a hoax. And the rules, being efficient, answer fast where they must and ignore the unaskable. Which sets our aim cleanly. To explain early brightness, follow the budget. Track where information flows, where redundancy multiplies, and where horizons fence access. The universe isn't clipping through walls. It's optimizing under constraints. Efficient, not fakery. The lensing, jungle, and selection landmines. While we were arguing about priors and spectra, something quieter kept tilting the board. Gravity itself was rearranging the scene. Lensing turns the universe into a hall of mirrors, and if you don't map the mirrors, you'll swear you've seen a giant where there's only a clever trick of glass. Macrolensing is the obvious culprit. A fat cluster sits in the foreground, its mass curving space like a magnifying glass. Background galaxies stretch into arcs, brightened by factors of a few to tens, and sneak above detection limits they'd never cross on their own. Without a lens model, you'll treat rare as common, tally up outliers as a census, and write a story the mass map will later delete. That's why teams near clusters built models first, iterating with spectroscopic redshifts of member galaxies, tightening the deflection field, and recalculating magnifications until bogus champions stepped down. Microlensing is sneakier. Stars and compact objects sprinkled through the lensing field add flickers on top of the macro boost. Over months, a tiny brightening can push a source over a threshold, biasing variability-selected samples toward lensed objects. If you then assume intrinsic brightness, you inflate mass and age. The fix is statistics. Model the microlens population, and fold the probability of small boosts into your counts. It doesn't erase the sources. It tempers how often you expect to see the spectacular. Then there's line-of-sight structure stacking. Not one big lens, but a handful of modest halos along the path, each adding 1% or 2% of magnification. Stack enough, and you've got a quiet bias. The bright tail of your sample is slightly more likely to be modestly lensed than you think. Survey teams ran ray tracing through cosmological simulations to estimate that tail, adding error bars not to a single object, but to the distribution itself. It's unromantic work. It's also the difference between the dawn is full of monsters, and the dawn has a long, bright tail. Selection biases don't need gravity to do damage. Eddington and Malmquist sit there like old accountants. When you select by flux, measurement scatters objects into your sample more than out. The steepness of the luminosity function then turns a few modest sources into many apparent brights. If you don't deconvolve measurement noise from the underlying distribution, the high luminosity counts swell. Teams went back, modeled the noise with injected sources, and pulled the function back to Earth. It shaved numbers, it didn't mow the forest. Deblending is a nightmare in crowded fields. Put two clumps within a point spread function, and your code must decide where one ends. Early pipelines, trained on Hubble-like images, misassigned flux in Webb's sharper, deeper views. One galaxy's light bled into another's footprint. A third vanished under a brighter neighbor's wings. A single misallocated halo of light can double an inferred mass or drag a photometric redshift into the wrong decade. Groups retrained deblenders on simulated JWST fields with realistic clumping, then reprocessed catalogs. Heads rolled, some celebrity objects shrank. The result wasn't a cleansing, it was a haircut. Meanwhile, the reanalysis loop became a constant. Preprints with thrilling counts, lens updates, calibration notes, revised catalogs, contrarian threads. Then, a quieter second cut that folded the learned biases in. This loop frustrated outsiders who wanted final answers yesterday. Inside, it felt like progress. Downshifts where lensing fooled you, upshifts where new spectra nailed a break, and a middle that kept its shape. Early galaxies still bright, still compact, still more common than smooth models promised. Human microstory. A lensing team posts a revised magnification map for a cluster. An object that looked like a record setter drops by a factor of 4 in intrinsic brightness. The discovery team grimaces, updates the plot, and keeps the point. Still high redshift, still compact, still busy. Across town, a blank field group runs injection recovery tests, and realizes their pipeline promoted more noise bumps than they thought in the faintest bin. They tighten their criteria, lose a few candidates, and nudge their luminosity function down. The slope changes. The story doesn't reverse. Lensing also giveth. Without it, some of the best confirmed high redshift spectra wouldn't exist. Magnification turned whispers into measurable lines. That duality is the jungle's rule. If you map the thorns, you can use them to climb. The same goes for selection. Compact starbursts and strong-line emitters get in first because they pass thresholds. That's fine, as long as you remember you're building a picture from the loudest voices. With time, deeper exposures and longer wavelengths pull the quieter majority into view, and the population fills in around the early extremes. The lesson is don't trust the dawn. It's don't trust your first draft. Bias will nudge your hand. Gravity will tilt the page. The fix is unglamorous. Calibrate, simulate, inject, recover, reweight, and be ruthless about how you count. When you do, the early crowd thins without vanishing. Some sources step off the podium. Enough stay in the race to keep you honest. Here's the stakes line again. If you clear the lensing jungle and diffuse the landmines, any galaxy still standing with a clean spectrum and a calibrated brightness is a demand. Not for new anchors, but for faster channels, burstier lives, and colder eyes on our assumptions. Because once the mirrors are mapped, the light has nowhere to hide. Rewriting the early chapters. To rewrite the first chapters without tearing out the binding, you start with clocks. Reionization isn't a vibe, it's a phase change, when neutral hydrogen gave way to an ionized universe. Quasars at Z6 hinted at late pockets, but 21-centimeter experiments and quasar-damping wings bracket the window more tightly. The lights flicked on around Z10 and were mostly on by Z tilde6. Webb's crowded dawn pushes the first sparks earlier, but stays inside those brackets if you let brightness come in bursts. That means more ionizing photons in less time, delivered by compact, intense episodes rather than leisurely ramps. Now tie star formation histories to metals and dust. Metal lines in early spectra say enrichment happened fast. You don't get strong O Roman 3 and neon without short-lived massive stars detonating on schedule. Dust in some Z10 sources says supernovae were grinding carbon and silicates quickly, enough to redden light paths and reprocess UV into infrared within a few 100 million years. That doesn't break the clock. It compresses it. Top-heavy stars dump heavy elements, dust changes cooling channels, and the second generation forms under different rules. Cooler, clumpier, quicker collapses. Semi-analytic models and hydro sims follow, then flinched. Old recipes that smeared star formation into smooth curves missed what bursty lives do to light. Update feedback to act in pulses. Allow clumps to form and shred. Switch on radiative transfer that actually feels the hard spectra of metal-poor stars. And the same dark matter scaffolding builds brighter beacons earlier. Slide the IMF heavier in pristine pockets. Add a channel for direct collapse black holes in clustered neighborhoods with strong UV backgrounds. Dial Super Reddington episodes to duty cycles that self-regulate. Suddenly, the catalog of impossible sources looks like the tail of a distribution we'd ignored. Predictions crystallized into signatures you could test. Compact sizes at the diffraction limit, half-light radii that refuse to sprawl. Bursty star formation histories imprinted in spectral energy distributions. Blue continua with superimposed nebular excess. Bomber breaks that flicker as populations age days to decades in cosmic time. Strong rest frame optical lines. O Roman 3, H beta, towering over continuum. High ionization parameters, weird line ratios that whisper low metallicity and hard radiation fields. These weren't speculative bullet points, they were Webb's shopping list. And Webb started checking boxes. Microstory. A modeler prints a grid of SCDs with bursty tracks, pins them beside spectra from MIRI and NIRSpec, and watches data points fall on the paths they drew months ago. They don't crow. They underline a line in their code. Allow duty cycles scatter, then send a message to a colleague. Let's push to ALMA for dust mass. Bet the grains are young. Reionization timing sharpened with those checks. If bursts dominate, ionizing output spikes above smooth expectations for the same stellar mass. Tie that to clustering, biased peaks where halos huddle, and you get overlapping ionized bubbles earlier without saturating the entire sky too soon. 21-centimeter constraints then force discipline. You can't ionize the world by Z12 if the radio sky says otherwise. The fix is geography. Patches light early, percolate, then coalesce by Z67. JWST finds the patch edges. Radio arrays promise the weather map. Metallicity and dust trends added weight. Early oxygen is high enough to light lines, but overall metals remain low. That's consistent with a few generations of massive stars, not a settled metal-rich milieu. Dust masses inferred from far IR limits and line ratios vary wildly. Exactly what you expect if some regions sit post-supernova, others pre-enrichment. The result is messy, not broken. That mess is how you get both blue, line-dominated SEDs and reddened, hidden starbursts in the same epoch. Hydrodynamic simulations rewrote their glossaries. Smooth accretion gave way to cold streams feeding clumps. Feedback subgrid moved from average heat dumps to momentum kicks that carved channels and precondition inflows. Resolution jumped, letting disks shear into bars and rings at lower masses and higher redshifts than Hubble-era art suggested. Some runs birthed unnervingly mature spirals by Z-34, Aleknanda's older cousin, without cheating gravity. Others piled light into knots that would look like Webb's compact jewels if you dimmed them by 1 plus Z, 4. And then came the quiet win, predictions that met patterns. Put a bursty, top-heavy metal-poor model on a catalog and it forecast the right fraction of strong-line emitters, the right sizes at given luminosities, the right clustering strength for the brightest. Webb found them. Counterexamples remained, outliers that forced sharper code, contaminants that spectra demoted, but the mean shifted. The lie turned into lag. Theory catching up to instrumentation with physics we'd always had, now allowed to run. Human beat. A PhD defense slide shows a before and after luminosity function. The old curve misses the bright end. The new one, with duty cycles and lens corrections, kisses the points. Someone in the back mutters, "About time," and the advisor smiles in a way that says they didn't sleep much last year. So rewriting doesn't mean a bonfire. It means bringing reionization clocks, metallicity, dust, feedback, and growth channels into the same room and letting them argue until the spectra stop rolling their eyes. It means trusting the anchors while letting galaxies live fast. It means prediction first, compact, bursty, strong line, found. And it sets up the only honest next question. If the first chapters are tighter and louder, what exactly does that do to the story we tell about the Bang itself? What the Big Bang is a lie really means. Let's say it flat. The lie isn't expansion or relic light or early chemistry. The lie is the cartoon we turned into curriculum, a fireball in empty space, a single picture origin, a neat ramp of growth that never tripped. Pop culture sold an explosion. Physics describes space-time evolving, cooling, and writing structure from a sparse instruction set. Webb didn't break the Bang. It broke the bedtime story. Start with the split between origin and expansion. In classrooms and thumbnails, the Big Bang gets framed as a blast, but there's no center in space and no outside to blow into. What expanded was the metric, the distance between comoving markers, stretching the wavelengths of light and diluting energy densities. That's why the CMB looks the same in all directions. We're not seeing shrapnel. We're seeing the last light from a hot, uniform plasma as it thinned and cooled. Call it a beginning if you like. Just don't call it an explosion. So what must go? Naive timelines. The assumption that galaxies cruised politely into maturity. The habit of fitting smooth star formation histories and late-time IMFs onto epochs that rewarded bursts, top-heavy stars, and fast black hole feeding. The reflex to treat photometric redshifts as gospel until someone flips on a spectrograph. And the insistence that if something is bright early, cosmology must be wrong. That's not skepticism. That's impatience masquerading as critique. What stays? The expansion history etched in the CMB and bow. The relic radiation itself with acoustic peaks that don't budge when headlines do. Primordial abundances that lock the early density and rate. The fence is firm. Any replacement lives inside it or dies on contact. You can add an early dark energy tweak to ease attention. You can adjust neutrino physics within bounds. You can let gravity whisper differently on small scales. But you don't get to erase the drumbeat and keep the dance. Now, about those replacements people like to pull off the shelf when lie trends. Cyclic universes, endless eons handing off through conformal rescalings, are elegant math with little data leverage right now. Bounces that turn a crunch into a bang avoid singularities in some models, but they still have to seed nearly scale-invariant fluctuations and thread the peak pattern. Emergent scenarios, where spacetime condenses out of microstructure, shift Y to a deeper layer. They don't hand you an alternate sky for free. The data-friendly versions are the ones that reproduce the anchors and only tilt the corners. Subtle pre-recombination energy, gravity tweaks that leave the sound horizon intact, inflationary variants with fewer knobs. Everything else is poetry until it fits 3 plots at once. Here's the human part. We wanted the origin story to sit still because still stories comfort us. Once there was nothing, then everything, clean. But the closer we look, the less those words carry. Nothing in the philosophical sense never shows up in an equation. The quietest state we can write still has fields, fluctuations, horizons. The universe we test started hot, dense, and simple, then cooled into complexity fast in some neighborhoods. If you need meaning from that, take this. Simplicity gave you permission. Complexity asked you to hurry. So what does lie mean, used responsibly? It's a label for our narrative lag, where explanation turned into repetition. It's a nudge to break the habit of swapping models when we should swap priors. It's a warning that communication choices can calcify into dogma while the instruments keep moving. The Big Bang isn't a doctrine. It's a scaffold tested by independent fossils. The lie is pretending the scaffold already came with furniture. What replaces the origin story isn't a rival myth. It's a frame that separates anchors from improvisation. The anchors tell you the stage lights, the set size, the opening chord. The improvisation is galaxies sprinting, stalling, and screaming back to life. Black holes skipping rungs, stars biasing heavy feedback punching holes and then pouring fuel. You don't downgrade the play because the actors surprised you. You update the program. That leaves a last, uncomfortable truth. If stories break, institutions either adapt or fracture. Watch what moves next: grant calls that fund bursty physics and early black hole growth, short-form explainers that pre-bunk selection traps, collaborations that merge CMB discipline with JWST chaos. The origin we hold isn't threatened by speed. Our storytelling is. The real fix isn't louder certainty. It's better receipts and a willingness to retire the cartoon. The platform problem: why doubt outruns data. While the anchors hold and the physics tightens, something else keeps slipping the leash: how the story spreads. The platforms most people use to learn about space don't reward calibration or caveats. They reward frictionless emotion. Doubt runs on a 15-second fuel. Data needs 15 minutes and links nobody clicks. Here's the loop in practice. A clip claims Webb broke the Big Bang. It packages a photometric candidate at Z16 as certainty, drops a soundtrack, and points to a plot with no axes. The algorithm sees watch time and shares. Meanwhile, the re-reduction that moved that source to Z5 arrives 3 months later behind a paywalled PDF, or on archive with a title that won't fit a thumbnail. The correction is careful and dull. The original lives forever. It isn't just speed, it's structure. Recommendation engines learn your curiosity, then drag it toward the loudest answers to it. Watch a segment about early galaxies, you get served another about impossible spirals. Click that, the next hop is the Big Bang is a hoax, then NASA hides the truth. None of that needs malice. It's the math of engagement. Surprise outperforms nuance. Suspicion feels like agency. And once you're in that lane, the platform assumes you want more. There's also a trust problem tone built. When institutions used cautious language to avoid setting off alarms, audiences heard hedging. When the same institutions pivoted later, because the H tension survived upgrades, because some high Z sources stayed high, audiences remembered the earlier calm and called it spin. The mismatch is sharpest for students who see spectacular JWST images on one app and slow, sober graphs on another. One feels alive, the other feels like homework. Guess which thread people follow? Creators trying to bridge the gap run into a different wall. Format. You can't show an 8 sigma Cepheid calibration result in 30 seconds without faking certainty. You can hint at the punchline. JWST confirms HST's local distance ladder, but the proof is in plots that don't animate well. Meanwhile, a conspiratorial short can splice a grainy Apollo clip with a modern studio shot and imply a lie without claiming one. The ambiguity is the content. The correction is a lecture. Synthetic media turned the screw. Generators make plausible telescope imagery on tap, nebulae with JWST-style diffraction spikes, lensed arcs of things that don't exist. Drop those into a quick take and the vibe of authenticity transfers. The audience can't vet file headers or calibration logs. Even trained eyes sometimes hesitate. That uncertainty doesn't prove fraud. It dilutes trust. In that fog, real anomalies and fake ones feel the same. Then there's identity. Disbelief online isn't only about claims, it's about belonging. Comment threads become communities where seeing through lies is the badge. Leaving the claim risks leaving the group. So a careful correction isn't just a fact to weigh, it's an invitation to lose friends. That's not a scientific problem, it's a social one. And it explains why evidence that persuades a lab room bounces off a feed. So what actually works? Pre-bunking beats debunking. Show the trick before the trick shows up. Strong lines faking distance, lensing turning rare into common, photometric priors nudging mass. Then when a flashy clip leans on those exact moves, the viewer recognizes the pattern and pauses. Hands-on beats passive. Let people slider a template from smooth to bursty and watch inferred mass drop. Let them toggle lens magnification and see counts shift. A minute with a tool outperforms a page of prose. Shorts can carry truth if you treat them as hooks, not proofs. One clean headline. This candidate fell from Z16 to Z5 after spectra. Hear why that's good. Then a ladder to a longer piece that walks the path. The tone matters. Admit uncertainty fast. Name the failure modes before someone else does. People smell confidence games. They lean toward voices that say, here, what would break this. Cross-institution receipts help. A JWST spectrum with a MIRI confirmation. A lens model updated with independent NIRS-spec redshifts. A Daisy bow point overlaying a Planck fit curve. Put logos side by side and translate the jargon just enough. A chorus of methods forces the algorithm to admit more than one song. There's also the unglamorous fix, archive design. Make calibration notes readable. Put interactive figures beside PDFs. Let a teenager on a phone drag the Lyman break across filters and watch the redshift likelihood spike. If evidence is a museum, stop hiding the exhibits behind docents. Put the artifacts under glass where hands can hover. Human moment. A teacher plays 2 clips in class. One viral Big Bang is dead, one dry seminar cut. Then they open a browser and pull up an interactive fit for Jade's GSZ14. The students slide a line, watch the break lock, and ask the best question in science. Okay, what would fool this? The room hums. That's the race you can win, not against an algorithm, but against passivity. Because doubt will always outrun data on platforms tuned for velocity. So change the race. Move the finish line from persuasion to participation. Give people tools, not just takes. Show the ledger, not just the label. Make the truth feel interactive, not inert. Then the next time a spectrum drops at 2 a.m., it won't have to fight for 15 seconds. It will have an audience trained to ask for the plot. The new playbook, radical transparency, smart drama. If doubt sprints and data jogs, stop trying to catch it from behind. Change shoes. Radical transparency first, then smart drama shaped by how people actually watch. Start with pre-bunking. Don't wait for the viral misread. Walk viewers through the tricks before the trick shows up. Show in 30 seconds how a strong Roman 3 line can flood a broadband filter and fake extreme distance. Swipe to lensing maps. Here's how a cluster magnifies rare things into common. Tap a slider. Smooth star formation fit implies big mass. Bursty fit cuts that mass in half and keeps the spectrum honest. End with a promise. When our new spectrum lands next week, we'll see which path reality chose. You inoculate before infection. You set the hook without faking certainty. Then open the ledger. Put the raw behind the claims in formats people can touch. An interactive plot where you drag a break across filters and watch the redshift likelihood spike. A zoomable lens model with magnification contours that switch as you toggle member galaxy redshifts. A spectrum overlay that snaps MIRI lines onto NIR-spec continuum with a click. Not just a DOI in fine print, an artifact on the table. Here's the file. Here's the fit. Here are the assumptions. Break them if you can. That tone doesn't dare the audience, it drafts them. Short form becomes your on-ramp, not your court of law. One crisp truth per clip. JWST confirmed Hubble's local distance ladder, so the Hubble tension didn't go away. This Z-12 candidate fell to -5 after spectra. Why, that's good science, not a scandal. This other one held a -14. Here, S the break, here are the mid-er lines. Every short links to a longer piece where receipts live. You treat shorts as invitations, not verdicts. Admit uncertainty fast. Make it a feature. Lower third labels that read confirmed. Z equals 13, 9 plus or minus, 2 or candidate, photometric high line contamination risk. Visual traffic lights, green for spectra, yellow for strong photo, Z with consistent templates, red for likely interloper. The badge builds trust because you're saying the quiet parts out loud. When the color changes, you show it changing. Same card, updated stamp, no defensiveness. Turn calibration into content. A 2-minute how 0 points move your galaxy with before-after thumbnails flipping in time with the beat. A side-by-side of debunders wrestling with crowded fields, old code V's retrained, and how that one change moved a catalog's bright tail. People love craft videos. Give them the craft of astronomy. The message under the edits. It got cleaner, and here's why the story didn't reverse. Cross-institution confirmations deserve staging. Put multiple logos on one screen. JWST spectra, ALMA dust limits, DAISY bow overlays, ACT/Planck peak fits, and narrate how independent tools constrain the same picture. You're not flexing brands. You're manufacturing consensus in public. When different instruments say the same thing, you've preempted the one lab's pipeline dodge. Build the browser lab you wish you'd had at 16. A light, fast archive where every headline object has the image cutout, the spectrum, the fit toggles, the lensing overlay, the simulation analog you can spin. 2 clicks from curiosity to causality. No sign-up, no jargon gate. It won't trend, but it will anchor the curious who always return with questions the algorithm can't answer. Tell micro stories that carry receipts. This source fell, here's the spectrum that moved it and the template that fooled us. This one held, here, S the MIRI line that locked the door. This lens model updated, here, S the magnification correction and why your count shifted. Drama isn't shouting. It's tension resolved on screen. Pre-register analyzes when you can. Here's our plan, our priors, our failure modes. Then publish the result against the promise. It looks like honesty because it is. It also blunts the hit job when an answer moves. You already said what would break you. Now you show you weren't broken. Recruit the audience with tools, not takes. Think this object is at Z-12. Drag the break past F150W and show us how you fit the lines. Convinced lensing inflated our counts. Toggle this exact mass map and send your distribution. Turn critique into co-work. The loudest skeptic calms when they can poke the thing itself. Roll out a shared style guide. Visual standards for confidence badges, axis-labeled plots, color maps that don't lie, and a banned list for graph crimes. When dozens of teams present differently sourced results the same way, the public starts to read plots like road signs. That's culture, not PR. Finally, center the meaning without shrinking the facts. Anchors hold, Galaxies sprint. Our job is to show you both in the formats you already use. Radical transparency builds the floor. Smart drama keeps people in the room. The next spectrum still arrives at 2 a.m. It should never have to fight the algorithm alone. Living with a moving origin story. If the beginning keeps shifting under better light, how do you live with that? Start small. Agency in a finite bandwidth cosmos isn't about controlling the ocean. It's about steering the currents inside your horizon. You change what you can entangle with, tools you build, data you share, habits you copy. That's not metaphor, it's physics. Facts stabilize when interactions spread and get recorded redundantly. So choose which traces you amplify. Meaning works the same way. Ideas become real when they're copied well. A clear plot with labeled axes, a transparent fit with toggles, a public ledger that others can check. Those produce redundancy. The more fragments carry the same story, the more objective it becomes. That's decoherence scaled to culture. A speculation whispered once stays fragile. A tested result mirrored across instruments and archives hardens into the record. Resilience beats certainty because the timeline flexes while the anchors hold. Light elements, acoustic peaks bow, they're the guardrails, everything else breathes. So you build practices that can bend, priors that update, pipelines that log changes, figures that keep old versions visible. If a candidate falls, the method survives. If a surprise sticks, the method scales. That's how you stop mistaking your favorite fit for the universe. Curiosity drives that engine, not as a slogan but as a habit loop. Ask what would fool this spectrum. List the failure modes before you publish. Invite the strongest counterexample and hand it your tools. When the result stands, it earns trust. When it moves, you show the move. The point isn't to never be wrong. It's to be wrong in public fast and with receipts. Human moment. A postdoc in a windowless office rewrites a figure legend at 1 a.m. Adds a confidence badge, links the raw file, notes the lens model version. It takes 3 minutes. A student in another city drags a slider on that plot the next day, sees the Lyman break lock and sends a question. 2 people who will never meet just entangled their work. That's meaning via redundancy. Living with a moving origin story also means translating that flexibility beyond the lab. If you teach, you stop treating the Big Bang like a perfect picture. You frame it as a scaffold tested by fossils, then show where the furniture is moving. Bursty histories, early black holes, top-heavy stars. You let students rehearse the failure modes, line contamination, lensing, priors, so that confirmations feel earned, not preached. If you create, you balance drama with discipline. Hooks invite, ledgers convince. You can say this spectrum either breaks our fit or proves a burst, then return with a plot. You can use shorts to open loops and long form to close them. You can admit uncertainty as a feature, not a flaw, badges, traffic lights, pre-registered plans matched to outcomes. The story becomes the process, not the boast. If you fund, you reward the behaviors that keep the floor solid. Pre-bunking, open tools, cross-instrument checks, adversarial collaboration. Surprise without receipts is candy. Surprise with receipts is nutrition. The first spikes views. The second builds culture. There's a personal angle too. In a cosmos bounded by horizons, your voice doesn't travel far, but the shells of what you do move at light speed forever. The code you publish, the figure you clean, the pre-bunk thread you write, those echo in other people's work long after the clip du jour evaporates. If you want meaning, optimize for echoes. What about belief? Drop the binary. Treat confidence like a posterior that moves as evidence arrives. Strongly favored survives known failure modes is a belief. Confirmed within this fence, Vulnerable to that test is a belief. Beautiful, but not yet measured, is a belief. Make those categories visible, and you free people from pretending certainty they don't have. The payoff is quiet. When the next dawn object lands and half the internet yells, your room doesn't flinch. You run the same checklists, post the same receipts, update the same badges, and slot the source where it belongs. Candidate, contender, confirmed. If it falls, you show the fall. If it holds, you widen the ledger. You let curiosity do the rest. Micro story before the term. A grad class debates whether a Z-14 photometric is real. Half argue lines faking distance, half note the mid-er excess. The instructor opens an interactive fit on the screen, toggles templates, then says, "What would break this?" The room fills a whiteboard with tests, MIRI lines, lens model updates, alternative priors. A week later, the spectrum arrives. One side smiles, the other nods. Everyone's model got sharper. So living with a moving origin story isn't resignation. It's craft. Agency is where your antennas reach. Meaning is redundancy you earn. Resilience is habits that flex without losing the fence. Curiosity is the engine that survives theory swaps. Keep those four, and a shifting prologue stops feeling like loss. It feels like work worth doing. The lie wasn't the beginning. It was letting the story stop evolving while the evidence kept talking. If you want the next chapter, subscribe and stick around. Our follow-up on dark energies ticking horizon drops next. Drop your wildest early